Alright, so you guys have been doing a lot of development yourselves in MakerChip. I think it's time to give you guys a break. I'll do a little bit of development myself, and you can kind of watch some of the things and learn from what I'm doing. So I've loaded here in MakerChip the example that we've been using with Pythagoras' theorem. So we've got our calc pipeline with stages 1, 2, 3 as we did before. I'm using A and B as 4-bit values. So there is no assignment in this code to A and B, and as we've seen before, we're just letting the environment make up values for these. I do have to give them a width, so they don't just default to a single bit value. So I'm giving that here, and I'm using a smaller width just to keep the values to small numbers, so it's easier to see what's going on in the waveform. And as I said before, the way we've configured the simulator, the compiler, it's automatically extending from, this is going to be 4 bits multiplied by 4 bits, which results in 8 bits, and then it's going to extend that with zeros. So this is our model. This is probably a good time to talk a little bit about the file structure. The first line of a TL-Verilog file specifies the file format. We're using TL-Verilog 1D as the latest, and this line also has a URL specified. This is essentially your link to documentation. The documentation lives at tlx.org. We can build this, we can have a header line that's just TLV version. By using M4 TLV version, we're enabling macro preprocessing using a macro language called M4. So macros, you're defining the text of the macro, and when you instantiate a macro that you've defined, you get the expanded text as you've defined for that macro. And the only place we're using that here is in line 4, where we have M4 MakerChip module. And we can see what the macro expands to by looking at the nav_TLV. So this is the interpreted version of the code. And the macro is expanded here to this module definition. So this is a system Verilog module definition that's expected by the MakerChip platform. And it's got inputs and outputs, including the clock, reset. For convenience, there's a cycle count. And then signals going, output signals from this module are passed and failed signals. And these signals control the simulation. If you look at the log, after Verilator runs, it reports passed. That's because this passed signal was asserted. And that was asserted because we have this statement: if the cycle count is greater than 30, then pass. And we can see in our waveform that we simulate for 30 cycles. And then we're done. So I'm going to walk through one of the tutorials. So this is a tutorial that uses the Pythagorean theorem example to accumulate distances. All right, so one computation of Pythagoras' theorem gives us one distance, c. And we're going to extend this logic, or use this little computation, to create a circuit that will accumulate a total distance. So we're going to do one calculation to get the first c value, first distance calculation. And then we're going to do another calculation and accumulate that distance. So add that new distance to the old distance. And again, do another calculation and accumulate. So to do this, our circuit is basically going to look like this. We've got our Pythagoras' theorem computation, and we're going to repeatedly do computations to get new distances. And each time we do, we're going to accumulate that distance into this total distance. So we want to, this total distance is state that we're going to keep updating. And as with all state, we need to reset that state. I'm going to simplify a little bit and just hook directly up to the reset input from the Verilog module that I just mentioned. But we're going to reset our total distance to 0. And then for each new distance that we get, we're going to add that new distance to our total distance. So that's this adder, and as long as we are valid, so we're going to allow valid computations, and we're going to allow cycles that are not valid. If the cycle's not valid, then we're just holding on to the distance. And if we do have a valid distance to compute and add, then we're selecting the result of the adder. Alright, so for each new valid computation that we perform, we're going to increment the total distance. We're going to add the new distance to the total distance, and that will become our new total distance, which we will retain as long as we have invalid cycles until the next valid cycle. So that's the circuit that I'm going to implement, and let's give ourselves some real estate here. I'll put this tutorial diagram down below. So also looking at the source code here, after the version line, I have this SV line, which says this code is just System Verilog code. It's basically telling the compiler, the TL Verilog compiler, don't do anything with this, just pass it along. This is a Verilog include statement to grab a definition for a square root module, and then we saw the macro definition, the module definition line here. And then the TL Verilog code is defined within the context of this System Verilog module. Okay, and we won't really look at the System Verilog. If you want to see the System Verilog code, you can look here. I'll just show this window so you can see, but we're not going to talk about the System Verilog because we're not teaching System Verilog in this course. But just to familiarize yourself with the window, if you do want to relate this to System Verilog, this is, maybe I can shrink this down. So this panel here is your source code, your TL Verilog source code, and that compiles to 2 System Verilog files. And then you've got some statistics up here about how much pain TL Verilog saved you. But anyway, like I said, I'm not going to focus on that. All right. Okay, so we have our starting code, and this is the Pythagoras' theorem circuit. And I'm going to do a couple things with that. So first of all, we're going to utilize the concept that we just learned, the when condition. So actually I'll put that inside the pipeline. So only when valid are we going to have a meaningful computation. And then I need to indent this under valid. And there's a handy dandy little shortcut, keyboard shortcut, control right brace, the right square brace will indent, and I can do left square brace to unindent. All right, so that gives me a valid condition. I'm not assigning valid. I'm going to let the platform make up a random valid signal for me, and I'm going to compile that. And you can see in the circuit diagram the valid signal is through dotted lines connected to these various expressions to indicate that that's their when condition. And we have a waveform that we can zoom in on and look at a computation here. So 2 inputs, A and B. I'm going to control click to select both. So we happen to have 2 values of hex 24, and that's resulting, oh, those are the squared, sorry, A and B. Control click. So there's no, since there's no assignment of A and B, I'm not getting the when condition here, unfortunately. But these are in cycle 1, which is 6, 6. Here becomes the hex 24 values here. So we have 6, 6, resulting in a C value of 8. So 2 distances of 6 resulting in 8 seems about right. All right, so we have our computation now with a valid, and Now I want to add in this purple logic here.